So first off, we'll start with Blake Corter, as mentioned, the Managing Director of Gradient Laboratories, who has a long history in the design engineering space with some very impressive companies. He'll be giving the opening keynote.
Hi, everybody. It is such a pleasure to be joining you today and kicking off this part of the conference. Hey, I'll lay a little historical groundwork for generative design and use that direction to try to extrapolate a little bit where it might be going. I will do this relatively broadly and abstractly. Hopefully everyone else will fit into the framework. A little bit about me and my company. Gradient Control Laboratories has existed for a few years. We're building next generation implicit modeling and collaborative tools for application development. So we mostly serve companies in the industry. My background, I started my career at PTC, started a company called Space Claim that became Ansys Discovery. Started working on the GrabCAD community at 200,000 users, left at over 15 million, but also we were acquired by Stratasys and built out GrabCAD Print and a number of other manufacturing-oriented products there. And then I joined NTOP to build the product that we now know as NTOP. Luke, my partner, has a similar background on the architectural side. So he built DesignScript and Dynamo, Autodesk's main generative design tools, before he went to Google to build the Dart programming language with some other members of the team. There he picked up Mariana Marasoyu, Dan Rubel. His company had been acquired by Google to make compliers. We have Steve DeMay on the team. If you've ever used SolidWorks eDrawings, remember that from the 2000s. He was the person who came up with that. Keegan McNamara is a mathematician who's been a venture capitalist, started a computer hardware company, and has done journalism and blockchain. A very interesting guy who's now working on our problems with us. And we have a support team as well. Our clients are doing amazing things in the advanced design and manufacturing. So the liquid print where I'm sitting today, they get some credit for the seat. They make silicone parts and giant aquariums of hair gel, so we can do lattices, make wonderful cushions, prosthetic devices, and maybe the odd handbag. This is a collaboration with Camperni. Variant 3D is launching in 2 weeks at Dwan's CD-FAM event in New York City. We're doing computational knitting, so we can make arbitrary surfaces with arbitrary patterns and arbitrary colors. It's one of the most intricate generative design tools I've ever made. Lattice Robot is a tool for doing empirical work with lattices. And Nexnilio is our latest company. They are working on agentic engineering at the product kind of PLM scale. So imagine millions of agents running around your products, helping debug them and find problems with them in collaboration with your engineers. So let's just sort of take a little look at what's going on in CAD, what kind of tools we have. I think there are really three different flavors of CAD as we have it today in terms of the parametricness of them, or how we express the parts in terms of a way that we how they, and the other in terms of numbers, let's say, and then the other is how much is this a manual process versus something that emerges from what I've done. And those are orthogonal axes. You might think, well, generating and parameters go together, and historically that's been somewhat the case, but there are plenty of things sort of off that diagonal axis. So, for example, we know tools like SolidWorks and Onshape with the history-based modeling paradigm. That's a generative paradigm. It's a parametric paradigm. But with architectural tools, it tends to be more explicit, and we generate walls by moving little line segments around. In surface engineering, we create curves and then create surfaces with those curves with relationships. So we can move the curves and the geometry updates. So it's explicit and generative, but not very parametric. On the other hand, with tools like Space Claim and direct modeling, we created tools that were parametric but had no history whatsoever. So the latest trend has been to make parameters not just things that affect the whole global design, but are field driven. And my work at Entopology, I think, it has taken a lot of things in that direction. But we see other tools, WOMP 3D and entertainment, and I think we'll see a lot more fields. The nice property of fields is that they unify a language for geometric modeling, physics, and manufacturing. And so you can work in one domain to do those three things. On the other hand, it's a lot of stuff to keep track of. So, looking back to the history of tools like Cythera and Grasshopper, there's kind of these patch panel interfaces, and I don't think the early telephone industry was the originator of these, but I think that it's interesting to think as a concept exercise, what's going on in this room. You might think, well, this is boring. These relatively unsophisticated operators are just connecting two people to each other. But what are those two people doing? Let's call those people kind of agent-like things. They're people, but maybe one person has some idea. Maybe the other person is giving feedback on that idea. I have a lot of phone calls that go that way. And if you think about that system in the language of machine learning, we call it a generative adversarial network. Right, we design machine learning systems to do that back and forth to make them better. Now here, there's not a lot of agency in connecting those two people, but there's something going on here where there's an emergent property of this room connecting those people and creating ideas. I also think it's interesting to look at the women who are behind at these gorgeous Art Deco quarter sawn oak desks. I've never sat at a desk that nice at work. What are they doing? And what are they? Does this maybe look kind of like a neural net? Maybe. Any as a point of departure, is this an early neural net where the networks are just made of humans? I don't know, but look, it's a thought exercise. If you want to do something a little bit more grounded, everybody in the CAD industry loves to talk about Ivan Sutherland and Sketchpad. It was really the greatest demo of all time. The guy invented graphical user interfaces just to do CAD. We have GUIs because of CAD. And look at this, the lines and points, that looks just like Grasshopper or Cythera. He was wiring them together. He was making lattices. It's actually interesting. What we call a lattice today are these networks. We tend to say this is a lattice. In math, it's just the set of points you'd use to transform things around. So that's why I use those two curves on the lattice. Yeah, it's mathematically correct. When we start using generation to produce shapes, I think Lindenmayer gets the first real, like there's others, some other shape grammars and things like that happen. But the idea that we're going to do biomimicry, we're going to try to use generative design to do things that are more complicated than we'd want to do as humans with these fractal-like trees. I think we have to give L Systems and Lindenmayer the credit for this. Although I don't think this approach has made it much into the kind of tools we use today. I think it really it set the vision, I think, more than anything else.
Hey, Blake.
Tools. I got to give credit to Nicholas Negroponte, who's an amazing guy, founded the Media Lab. Also, Wired was involved with Wired magazine, and I loved his article at the back in the 90s. He may be somewhat canceled. You can look up why. But in this case, we're going to give him some credit. I think it's interesting here to observe that he has an LLM style interface for humans. He has a procedural generative setup for the machine, and is trying to figure out how to get the human operator and the generative thing talking to each other. So this kind of thinking led to the Media Lab. And not to mention, I want a cool device with buttons like that for using CAD again. Those were trendy in the 70s and they took them away. But with all the keyboards kids are making these days, we're going to have CAD keyboards again. I'm working on it. Okay. So back to patch bays. Meanwhile, Wendy Carlos is recording Switched on Bach, which is just an amazing thing to listen to, using these Moog synthesizers and so forth at half speed. And it was incredible work, but very tedious to patch each one of these voices together on the machine. And so when people were enjoying their disco synthesizer stuff and getting into the 80s, people were like, hey, and personal computers were available. Maybe we can like digitize this like so many other things, drafting. We're all going to the computer. How we can get music to the computer? And starting with some research by Max Matthews, and then later Miller Paquette, sort of perfected this thing called Max MSP, which was a digital patch bay tool. And you put the keyboard and the reverb and all these things and make these awesome synthesizers, and MIDI was a big part of this. And this led the 80s music was powered by these kind of things. And at some point, someone's like, hey, we could get geometry of this and make cool visual effects too. And that's where jitter came in. And I'm going to credit this. There's a lot of other contemporaneous work, but this is the one tool I can point to that was very popular and crossed the gap between the sound temporal generative and geometric generative. And now we're using the first Grasshopper-like system to do geometry. Later in the 80s, a very interesting and somewhat awkward piece of software emerged called ProEngineer. I started my career at PTC in 1996. It still looked like this in those days. It introduced three ideas at once. One is that it's feature-based. There's a history of operations rather than just some big dumb lump of stuff you're looking at. That it's parametric, that there are these numbers we can use to edit what we've made. And that it's associative, that if you put the part in an assembly or in a drawing and make a mold with it, everything updates. I know everybody knows this nowadays, but it was a revolutionary idea at the time. PTC, I think, had one of the last great IPOs we saw in CAD. And this piece of software was really something else. The menus, incidentally, just to point out how interesting this was as a generative piece of technology, these menus that were famous for being awkward to use were actually, there was just one piece of code. The geometry kernel and the user interface were all written together into a giant executable. And when reporting a bug, you just tell them what menu you were on, and it was the same as a call stack. It was very hard to port this thing to Windows. And so later in the 90s, we see some other sort of CAD systems emerge, but Bentley Systems gets credit for doing I think the first mainstream product in generative architecture. They made a node-based tool for synthesizing things like skyscrapers and other repeating geometry. Very quickly, McNeil with Rhino copied them with Grasshopper. I should remember the name of the Grasshopper guy. But we saw kind of these two streams of kind of lower cost and easier to use tools emerging. One are the feature-based tools like SolidWorks and Inventor. And then on the more architectural side, in addition to the Grasshopper, of course, we have my buddy with Dynamo and DesignScript. To this day, I'm pretty sure DesignScript and Dynamo is the only one of these systems that handles first-class functions, where you can actually use it as a proper programming language rather than just like a synthesizer mixer. Just an aside. Some of that drives our work at Gradient Control these days as we try to improve upon this kind of first generation of simplicity. So that's sort of it takes a while for out of CAD as they're kind of the CAD and there's kind of a race to the bottom in pricing and distribution, and everyone's trying to convert to SaaS. And so we don't see a lot of innovation until a bunch of stuff starts happening with the additive manufacturing revolution. One, again, I had the opportunity to contribute to was NTOP and field-driven design. And today NTOP is making aircraft and doing Class A surfacing. I didn't think I would see this happen in my lifetime, but for this kind of vehicle design work, we're making really high quality engineering surfaces and synthesizing vehicles at a concept scales, and there's a market for this stuff these days. So it's been very exciting to see NTOP go from a lattice kind of design tool and advanced manufacturing tool to a vehicle scale CAD application, and that's pretty neat. The other thing that I think is pretty amazing is what Moritz did with Cynera Elise, which is to say that really embraced the Grasshopper style of design, but put Parasolid in there. And I had been wanting for decades a Parasolid and Grasshopper, decade and a half, let's say, and to have it here, not just like that, but with a better thought out user interface. You can, I'm here today because I love this product, just so you know. If I have to do history-based B-reps, this is my first choice. One other generative application to sort of show you where trends are going. HiArc, my friend Peter Boyer was the CTO, but also these guys have done very well doing generative buildings. You need the drawings, you need the building. Instead of hiring an architect, you use this thing and design it. But what's interesting about this, and again, starting to look towards the future, is that these guys don't sell this software as like SaaS, right? We're going to have You don't buy the software, you don't pay an annual fee for it, you just use it to build houses. And yeah, I think you're going to pay for the result, but the way these guys make money is by selling you shingles and things like that. They put so much value into integrated systems that it's actually a better business than most CAD businesses. And I realize I'm not speaking to industry people here, but when you say, well, what are my vendors going to be doing? You see this all these new AI companies coming out. Watch the ones that are creating new businesses, not just the ones that are doing something that people have been doing for a long time faster. Those are the ones where you might see some interesting innovation. I think Hierarch is an example of that kind of innovation. Okay, so in the remaining, I think I've got about 5 more minutes here. Let's look to the future. The first thing I'll point out is that there's kind of 3 trends that we see going on in how geometry and AI are coming together. One, I'll call LLM-based scripting. I think we were talking about this yesterday, and John called it text-to-CAD. Text-to-CAD does seem problematic when you think about it at that simple level. My challenge with it is more that if we're using LLMs to make scripts, and those scripts are using things like BREP kernels to make the parts, there's a huge disconnection across there. And I'll explain why that's problematic in a second. On the other side of things, we see some really exciting ways of representing geometry with neural fields and radiance fields. And there's been tons and tons of variational autoencoders, lots of cool ways of using machine learning tools to represent shapes. You can even do it for mechanical design, but how do you what are you training it on? What's coming out? It's a bit nebulous. So at gradient control, we focus our energy at what we call geometry as code, where instead of having script to make something at a bit of arm's length, the code is the shape. And I'm not going to go into the math details of that now, but it allows us to do things like take advantage of modern compilers and language tools to create ease of use in geometric modeling. And we mostly use this in manufacturing and applications where you want things to work every time. You never want it to say, I can't do that. And to throw out a big word, when you're looking at systems, ask yourself, does this system most tightly represent the thing that it's making? There's this measurement called Kolmogorov complexity, where what is the simplest statement I can use to represent something? If I have a million ones in a row, I can say that instead of saying 1 a million times. Which of these representations are most likely to capture engineering and design intent? We're betting on the middle one. And so the other thing we're betting on is real data. It's pretty easy to set up a simulation tool and create a lot of baloney and then throw a model on it. But what are you really trying to achieve? And so when looking at AI and ML, I look for knowledge first, machine learning second. And if you have to generate a bunch of synthetic data, I got a lot of questions, due diligence questions about whether I can actually use that tool for engineering. So the way I see it is that data is the most precious thing, and especially hard to come by in engineering because most engineering firms think that their drawings and so forth are really important IP, and they're unlikely to share them with anyone, let it get leaked, or you train it with how to do your IP, and then you sell to your competitor. Next thing you know, no one even knows, but your trade secrets are being implemented on someone else's product. It's a legitimate concern. So if you have real data, that's golden. How can we use that? FEA and CFD are useful, but now you have to have people that understand the assumptions, and that's always more expensive to use. And you are making assumptions. What is my Reynolds number and so forth. And then finally, maybe you can put some tools on top of it. Now, those are kind of they're the cheapest to deploy these days, and they come with the most assumptions. And so one little message I have in terms of the world of physics here is look at the folks who are actually doing real physics faster. I have friends at Intact Solutions and Feather. At Entopology, we help fund Rohan Sahani's work on March on Walk on Cubes. Sorry, Walk on Spheres. To do Monte Carlo-based simulation, which is fascinating. And ANSYS Discovery and SimScale are both doing amazing things with meshing and real-time simulation to increase the amount of stuff we can do. I would go with those guys rather than something else on top. I would use Synera to model something that I understand well rather than something that someone else did for me. And so when we look at how agents are going to work, I think we have to look at what engineering is. And fundamentally, with any generative tool, we're taking a set of parameters, including the program itself, because the program is a parameter. And we're then evaluating the fitness. How much does it cost? Is it going to break? How good does it look? And the job of a generative design tool is to understand that matrix of combinations. For every fitness, every parameter might affect it. What is that sensitivity? We call that matrix the design Jacobian, and we update it based on that intelligence. And so the thing that I would encourage everyone to do as they're looking at the new world of machine learning and understanding how things apply is to make a diagram. Think about what's flowing to what in what order. Can I subdivide that thing? Can I throw that thing out? Is that thing going to be important? Draw these diagrams. Tools like Synera are good for it. There are other ways of doing it. I'm particularly fond of some thinking from the Topos Institute folks, Brendan Fong and crew, who have a wonderful book on applied category thinking, where you can get really abstract and understand why you need to be abstract to understand some nuances. If I were you, I would spend time in this department to understand where we can deploy AI and ML along with people successfully together. And on that note, here's a Gartner hype curve for the things I talked about, and I'd be happy to take some questions.
Okay, thank you, Blake. It's super interesting. The pushback on synthetic data for training ML is something we've seen in a lot of different areas, and the ML being trained on the shortcuts people have taken rather than the results of the simulation is something that we've seen crop up. So it's interesting to see that sort of pulled out, and the way in which we're sort of like talking about a systems level approach to both design, engineering, and manufacturing simultaneously, and how we pull those together is something that we're going to hear from Moritz from Synera. So next up we have, and we'll go for questions in the panel discussion. So we don't have any in the questions yet. If you have a question for Blake, please put it in the Q&A. We'll get to it when he comes back from his meeting and we have the panel discussion. So super interesting. Thank you for your time, Blake. It was cool. We'll talk more later. And looking forward to seeing you at CDFAM.